Hello everyone, my name is Zhou Zhang. Today I'm talking about a persistent learned index for non-volatile memory. My report mainly includes background and peeling structure. I start by introducing the learned index. Given a key, an index quickly finds the key's position in the dataset. The idea of the learned index is to replace traditional index structures with machine learning models. The idea stems from the observation that machine learning models have the same capabilities as B-plus trees. For example, in the left figure, the B-plus tree does not predict the precise location of the key, but rather an ambiguous location. The machine learning model can also provide a similar function. It can save the maximum error of the model during training, and then perform a local search within the maximum error range, and the data will be found. Therefore, it is feasible to use machine learning models instead of B-plus trees. Learned index is more advanced than the B-plus tree in that the B-plus tree does not use any data distribution information, while the learned index learns the distribution regularities of the data. Generally, a learned index is an in-memory index. It organizes data sequentially. The range queries are supported. An initial attempt was to use a neural network as an index. However, the performance was not good. The main reason is that the calling overhead of the neural network is high. The training is expensive and it is impossible to achieve high prediction accuracy with a single model. Therefore, the learned index uses a hierarchical model structure, and the fossil layer has only one model, which is obtained by fitting the entire dataset. Each layer below has multiple models, and each model is obtained by fitting fragments of the dataset. The hierarchical structure makes it easier to achieve high accuracy. Compared with the B-plus tree, the space cost of the learned index is lower, and the query performance is higher. By analyzing the runtime states of the learned index, we get the main reasons for the better performance. Each leaf node of the learned index can store thousands or even hundreds of thousands of elements. The nodes are very large, so the index structure is very flat. And it has fewer pointers than B-plus trees, and fewer nodes need to be visited during the search process. By using model inference in the node, it can directly narrow the search range to dozens of elements. Since the performance bottleneck of indexing is not speed overhead, but memory access delay, the performance of the learned index is better. Next, introduce non-volatile memory. NVM has a data access latency close to that of DRAM. It is byte addressable and can store data persistently. The first commercial NVM Intel Optane DC persistent memory was launched in 2019. Unlike the index on DRAM, since NVM is a persistent device, the NVM index needs to consider the problem of crash consistency. Because the CPU memory controller will disrupt the order of write instructions. The solution to crash consistency is to use the CLWB instruction to force the cache line to be written back to NVM and use sFence to isolate the write instruction. This results in higher write costs for NVM. The main optimization goal of the NVM index is to reduce the number of CLWB instructions and the number of NVM block accesses. Current NVM indexes generally use techniques such as unordered nodes. which requires that the size of the nodes should not be too large. We hope to introduce the learned index in VM for higher performance and space efficiency. However, the nodes for the learned index are usually too large to use existing optimization techniques. Currently, Apex is the only known VM-oriented learned index. It is for VM and DRAM hybrid architecture. It caches nodes metadata in DRAM using accelerated structures, reducing VM block accesses. This makes it slow to recover from crashes. Research on learned indexes for VM-only architectures is missing. Next, introduce the structure of peeling. The index structure of peeling mainly contains three types of nodes, namely inner nodes, leaf nodes, and fast and fair. Fast and fair is an VM-oriented B+ tree that peeling uses to handle out-of-bounds insertion and data overflows. Peeling uses the optimum PLR algorithm to divide the datasets and train the models. Both inner nodes and leaf nodes use the model, and each node holds a linear regression model. Peeling adopts 4 key designs, including VM-aware data placements, locally ordered and globally ordered leaf nodes, storing model copies in parent nodes, and hierarchical insertion strategies. The leaf node structure of peeling is shown in the figure. Since the excess granularity of entire Optane DC percentage memory is 256 bytes, we align the node space and divide it into 256 bytes blocks. The first block is used as the node header to store node metadata, and the subsequent blocks are used to store data. Each block contains 15 leaf slots and a pointer to the overflow tree. Overflow trees are only created when needed. Peeling's leaf nodes use an VM-aware data placement strategy. When creating a leaf node, we allocate twice as much space for it to support subsequent insert operations, and extend the model's mapping range to the entire node's dataspace. Model is then used to predict the position of each key, and the key and the corresponding payload are inserted into any free slot in the predicted block. If the block has no free space, the data is inserted into the overflow tree. Leaf nodes are designed to be unordered within a block and ordered between blocks. The intra-block out-of-order can avoid extra data movement during inserts, since the model is monotonically increasing. Ordering between blocks is inherent. And within an inner node, peeling also aligns the node space and divides it into 256 bytes blocks. Each block contains 8 inner slots, and each inner slot is 32 bytes in size. As shown in the figure, an inner slot contains an 8-byte key and a pointer to a child node, and also contains a parameter of the child node, including the model slope and intercept, and the number of blocks of the child node. Using these three parameters, it is possible to predict the position of the key in a child node without needing to visit the header of the child node. An inner slot also contains bits marking the node type and the log status. On today's AMD and Intel architectures, only the lower 48 bits of a 64-bit pointer are valid, and we integrate these special bits into the invalid bits of the pointer. Peeling uses different insertion strategies for nodes at different layers. For leaf nodes, peeling uses a deterministic insertion strategy to ensure that new keys can be inserted into the index. For the parent node of the internode, uh, for the parent node of the leaf node, that is the lowest layer of inner nodes. Peeling uses an opportunistic insertion strategy. If there is a free slot in the inserted block, perform the insert operation. If there is no free slot, the insertion is discarded and the leaf node is treated as an orphan node. This strategy can prevent a large amount of data movement caused by one insertion and ensures that the parent node of the leaf node will not split, avoiding expensive cascade split operations. Therefore, no insert operations will occur in the upper layer of the parent node. Next, the operation implementation of peeling is introduced. Peeling supports point query, range query, upsert, delete, bulk load, and query recovery interfaces. The upsert operation adopts the query consistent write strategy based on significant 8 bytes, and only one CLWB instruction and one advanced instruction need to be used to complete the multi-word atomic write. The process of leaf node splitting involves multiple pointer updates, and we use redo logs to achieve split crash consistency. Besides, we monitor the number of orphan nodes. When the proportion of orphan nodes reaches a threshold, we rebuild the nodes in the upper layer in batches. Peeling uses optimistic concurrency control and fine-grained locks. Our key idea is to minimize the duration of locking the entire node and avoid access locks causing additional unbound block access. We carefully design multiple levels of locks and version numbers in global nodes and blocks. Finally, the experiment results are presented. And our server is configured with 1 TB NVM. The experiment uses a public map dataset, and the workloads are based on the YCSB workloads. The comparison indexes include 5 NVM-oriented indexes called Apex, PackTree, ROART, KLB-tree, and Fast and Fair. And on the OpenStreetMap dataset, peeling achieves the best performance on workloads with different read-write ratios. Although the read performance of peeling is lower than Apex when the number of threads is small, peeling has more robust scalability and the better performance when there are more than 20 threads. In terms of space efficiency, peeling's index structure size and fill rate are better than Apex, and the DRAM is not used. When recovering from a crash, peeling can go to work immediately, while Apex needs to wait more than 1.5 seconds. And that's all of my presentation. And thanks for listening.